All right, good afternoon. So back for Calc 2 here. So today we get to talk about integration by parts. It's always a fun thing to do. Okay. All right. So do you remember, right, we have the integral of 1 over x, right? And that was equal to the natural log x. Don't forget the opposite bias because, right, 1 over x looks something like this. We really don't know where we're integrating from, so it could be on the negative side, so that's why we have to have the opposite bias. And then plus c, of course, because it might be a vertical shift somewhere. Okay. So the question is, like, well, what do you do to integrate natural log? And the answer is obviously not 1 over x. Okay, the derivative of natural log, right, that was 1 over x. But the integral of natural log right now, that is unknown. Okay, so what we're going to do today is we're going to learn, well, how does this work? Okay, and what we're going to do is we're going to undo the product rule. Okay, so remember the product rule, right? I'm sure that this has been seared into your brains and you will never, ever, ever forget it, even after Alzheimer's rips away everything else in your head. Okay, so we have the derivative, right, of uv. So we have, this is derivative of the first times the second, so v du minus the first times the derivative of the second, right, u dv. And now we're going to undo it. So what do you do to undo it? So we're going to go ahead and take the integral, right, of dv, and that is equal to the integral of v du minus the integral of u. Oh, there's an, I'm talking about Alzheimer's ripping that out of your head. All right. And here we have fundamental theorem of calculus at work, so we just have VU. Okay. And that is equal to, here is VU plus UdV. All right? So there we go. And what we're going to say here is that, let's go ahead and do it this way. So what I'm going to do is I am going to put this piece, right, on the other side, this equal sign. So we're going to have the integral of, we have the integral of u dv, right, is equal to uv, and then this went over, minus integral of v du, right? And this is known as integration by parts. Okay, I'm going to tell you, do not memorize this formula. You've already gone through the trouble of memorizing it because you remember product rule. It's just which parts get put where, and it's really not that important. Okay, I'll show you how to set this thing up so that you will always get the formula and you don't have to worry about it so much. But memorizing this the way it is when you have product rule is kind of a silly thing. Don't waste your time memorizing when you already know. Okay. So what we need to do here, right, we have a UdV here. What we need to do, right, is select in our function, right, we have our integral of natural log x dx, and we need to select pieces here that are going to correspond to u and dv. So what we're going to do is we're going to say, well, here's u, here's dv. What do these equal? Well, how about we set u equal, we don't want to set dv equal to natural log because the next thing we have to do is integrate that. And that's what got us into this mess in the first place. So we're going to go ahead and say u is equal to the natural log of u. And du, right over here, is equal to 1 over x. dv, and what's left over? What the part that's left over is dx. Okay. So this is the canonical, this is the motivating problem for this. Unfortunately, it's got a really tricky piece to it, which is this thing right here. Okay, so it's allowed to pick dx as your extra part here. Okay, you want to integrate dx, right? We just get x. We're not going to worry about the c just yet. That's going to come in at the end. Okay, because you're going to have two c's and we're just going to combine them and make one c. So if you're worried about, like, well, there's a plus c here, like, technically yes, but we're going to put it in at the end. We're not going to put it in here. All right. So what we're going to do, here's how you deal with this formula here, right? Is we're going to have uv. So we're going to take this diagonal. So here's uv, which is x ln x minus integral of v du. So minus the integral of x times 1 over x. Technically, there's a dx here, there's a dx here. All right. Now, this is often an easier integral to do than the first one, right? So clearly, this one's a much easier one to do, right? This is a physics integral, man. This is awesome. Okay. And I say that not because I don't think physicists can integrate. I just see physicists do a lot of work, and they do a lot of work to end up integrating things like dx, okay, which is just absolutely awesome. All right. And we end up with x ln x minus x now plus c. Okay, you can factor this, right? The absolute values here, I suppose, because we integrated. Minus 1 plus c. Now, should we check it? Does it work? If I gave you the function, right? If you were in Calc 1 and I said, you know, here's my function, is x ln x minus x, and I said find y f prime, right? We'd have to end up using the product here, right? We'd have derivative of the first times the second plus the first times the derivative of the second minus no product rule, right? Just a minus there for derivatives, which would be minus 1. So we'd end up with, right, ln x. These guys cancel, so we'd have plus 1, minus 1, right? The derivative of c was 0. We don't have to worry about that. And that goes back to ln x. All right, so we've shown that, right? We integrate ln x, so we get x ln x minus x. And then we took the derivative of x ln x minus x, and we ended up with ln x again. But that is a process of integration by parts. Okay, so you're going to learn a lot of different integration techniques in this class. That's mostly what Calc 2 is integration techniques. So the first thing you always want to do is, can you integrate directly? Right? If I happen to give you something like secant squared, you're like, the integral of secant squared, derivative of tangent of secant squared, so clearly, right? So if you could do a direct integral, that's something you should probably do, right? Don't mess around. Like, it always amazes me, like in Calc 1, where they say find the derivative of this, and then people use the product rule to do it. I mean, you can, it will work. It's just, wow, that's, it's a long way around, because you should realize that that's just, it's going to be 10x no matter how you do it. Okay, so they'll do derivative of the first times the second plus the first times the derivative of the second, and it's like, really? Okay, but I get it. Okay, it's the first time you're learning it, you think, 5 times, that's a product, I should do this. Okay, but if you can integrate directly, good, do that. 2, how much practice have you had with U substitution so far? Yeah, quite a lot. So U substitution is your next choice, okay? And then you want to try integration by parts. Now, there's certain forms that have to be done by integration by parts, okay? If you have a polynomial times a transcendental function times an exponent, you have a polynomial times a logarithm, any kind of log, you have a polynomial times a trig function, you are going to be doing integration by parts. Okay, there's just certain forms that you will get to know to say, I'm going to have to do it this way. All right, but if you're just getting on integral and you don't really know, you try direct, then U substitution, then integration by parts. The other kind of weird thing about integration by parts is these, you're going to carve up your function into U and dv, and you're kind of carving puzzle pieces. Like those have to fit exactly, right? When I picked ln x dx, there was no manipulations, there was nothing else. It was just, right, ln x dx. You generally do not want to manipulate stuff in order to put it into integration by parts. You just want to do integration by parts with the pieces you have. You have to account for all of the pieces and then go with that. U substitution, you've done this, right? You've tied this thing into a knot before you integrate it. You know, you just think about the ones where they have the linear ones, and you have to turn around on themselves and go backwards and forth. There's all sorts of fun shenanigans that happen with U subs. But integration by parts, it's a more complicated thing. There's generally not any shenanigans when you're doing this. You're picking a U, you're picking a DV, and you're going. Okay, and that's how you set this stuff up. So these are pretty boring problems. Okay, as far as like once you've chosen your pieces, you put them, you put them in the box. Like, what do you mean the box? I mean the box. Okay, this is the box. And then you just go ahead and follow the instructions on the box. Okay, that's what you do with this thing. All right. So with that being said, we're going to go through a little bit of your homework here. We'll go through some of that, and then we'll probably do this again tomorrow because 7.1 is this is a pretty powerful integration tool. And I think we could devote 2 days. I think we're pretty much kind of caught up at this point. So we'll probably do this again tomorrow as well. Okay. So so here, right, already we have integration by parts. We have a polynomial times an exponential function. Okay, that's what this is going to do for us. So I normally would go through my little, well, can I just integrate this? In this case, no, right? I can't just integrate that. I don't have a good form. And I know that a polynomial times an exponential is automatically going to be an integration by parts problem. All right. Well, I mean, again, unless it's really like if you end up with like a e to the x squared and there's a 2x out here, just an x out here, like right? That's a u sub. That's not an integration by parts. Okay, so we're not talking about this one. But okay, so great. Pick your u, pick your dv. All right. This is not a rule that's going to last forever and ever and ever, but a guideline. So generally, whatever you pick for your u, your next step here is to take your du, right? So you want what you're picking to u, your derivative of that, you want that to be a little bit simpler. Okay. So of the two, which of these is getting reduced in power or getting to be a smaller function when you take its derivative? And that's going to be x, because the derivative is just going to be dx. Now for dv, right, e to the 2x, when I integrate this, if you have to go off to the side here and say, let's go off to the side. If you have to do a let t equal w, all right, equal 2x, and dt is equal to 2, and you put, right, you're going to do this, because I'm multiplying by 1, or, sorry, yeah, and now you've done 1/2 integral of e to the t dt, 1/2 e to the t, which is 1/2 e to the 2x. You go right ahead and do that. I never memorized this formula. Sometimes it shows. Maybe I should have, but I got enough stuff rattling up my head. As you practice these, you'll get a little bit faster at them. Okay. Normally, we say, always show your work. If you didn't show me this, I would, and maybe you did memorize it. I would just assume that you did. I would not question how you got from this point to that point. All right. It was just I got you. All right. So now what we're going to do is we're going to do crossover. And we have our v to u integral. Okay. So here's our uv, right? There it's 1/2 x e to the 2x. Right? You can make it a little bit fancy. Minus integral, right? 1/2 e to the 2x dx. Well, we just integrated that, right? Over here, we just integrated e to the 2x. I know what that is. That's 1/2 e to the 2x. So what we have here, right, we have 1/2 x e to the 2x minus 1/4 e to the 2x indefinite integral plus c. All right, and that would be our solution here. Okay, we could make this a little bit prettier. That's okay. We can put an e to the 2x out here, and we could have we could even put a 1/2, right? We could have an x. If I pull a half out of that, right, that's going to be 1/2. And then we could do plus c e to the negative 2x. Or you can put the c off to the side. Okay. People who write answer manuals are very bored people and will often write things out in a way that makes sense to them and not really care how it makes sense to you. So, well, at least the books I used, that's what they did. Okay, they're a little bit better now, but still, they do it the way they want to do it. And sometimes more than one person is working on it, so you get two different styles of people who like to write answers in different ways. So this is a perfectly fine answer. We'd be extremely happy with you if you got this problem and this is what you wrote down. That'd be great. Okay, so you don't have to make it fancy after the fact. All right, well, that seemed pretty tame. All right, why don't we look at another one? Right, here we have something a little bit more complicated. We have an x squared plus 8x cosine x. Okay, so here we go. We have an x squared plus 8x cosine x dx. All right, same idea here, right? What is going to get smaller when I take its derivative? Is that going to be cosine, or is that going to be this one? In this case, you know, there's a better choice, right? There's u is equal to x squared plus 8x. dv is equal to cosine x. Okay, dx, technically. Go ahead and take your derivative. So du is equal to 2x plus 8. And then v, right, we have to integrate cosine. What's the integral of cosine? I think that's going to be sine, right? If I take the derivative of sine, I get cosine. dx here, dx. Right? So our what we're having here, right, is we have x squared plus 8 times, right? Here's our uv, so here's our cross the box here, and we're going to do that. So we have x squared plus 8x times sine x, right, minus integral, right, this is an equal sign. The hardest part, well, generally the hardest part of this problem is keeping sure your signs, SIGN signs, are correct and dealing with all of this. All right, so uv, v, du. Okay, 2x plus 8. Well, unfortunately, we kind of have the same problem here, don't we? So we have another situation here. Okay, we have another situation here. We have a polynomial times of trig function. So as much fun as doing integration by parts was once, we're going to do it again. Okay, so in this case, again, we're going to say let u equal 2x plus 8, and then du would be 2. Okay. You can technically separate this out and integrate the 8 sine x by itself. That's not going to hurt anything. But since they gave it to us as a kind of a package deal, I'm just going to go ahead and deal with it as a package. What's the integral of sine, right? Isn't it negative cosine x, right? Derivative of cosine is going to be negative sine. So I've got to put like a negative here. Okay. So now, right, we've got this little part of the problem. I didn't include the negative sign. That's in the previous thing. I tried to do it on my box so that my little grouping so that I could push this back into this spot. All right. So this here, right, this is going to be negative 2x plus 8 cosine x, right, minus integral. And then we have, right, we have negative cosine x times 2. So this little spot here, right, because we're working this little mini problem here, this is minus 2x plus 8 cosine x. we have negative and negative, so let's make sure we've got that sorted out. All right. And then we have to integrate cosine x. Well, the integral of cosine x, I think that's going to go back to being sine x. So we're just going to have a 2 sine x here. Okay, derivative of sine is cosine. Plus c eventually. Again, we'll put the plus c in. We'll tack that on at the end here. Okay. So we've got negative 2x plus 8 cosine x plus, right? Because now it's plus, all of that. And we're going to go back into here, right? And we're going to say, okay, great, this is back to blue. So this is x squared plus 8x, right? X squared plus 8x sine x, all right? And then we have a minus here, right? There's a minus in front of this. So we have plus 2x plus 8 cosine x minus 2 sine x plus c, right? And this is fantastic. If this is where you are, great. I'm so happy. I'm going to do one more thing here and just combine the sines and the cosines. So we have, what do we have? We have x squared plus 8x, right? X squared plus 8x minus 2, and this is all times my sine x's, and then plus 2x plus 8 times my cosine x plus c. So why'd you do that? Because it looks prettier than just having all of this stuff like this. Okay, honestly, my aesthetic says group your sines up and group your cosines up. But if you left it as was, like, I'm not, I don't think anybody's going to complain. Okay. If you ever get to take linear algebra, fun class, you're going to learn about, you might have more of an appreciation of why you would group them together like this. Okay, but that's later. Okay, so that's integration by parts of a slightly more complicated problem. All right, so let's take a look. I'm going to wait on the inverse ones for a little bit. I was going to hold off on that one. We'll talk about this one here. Okay. So integrate, again, here is, right, the natural log of the square root of x. Are any of these like, dang it, they're not. The business calculus class has the orders of things differently. It introduces integration by parts, and then it introduces rotations of a solid, and that gives you can have slightly more interesting rotations around a solid. You guys don't get that because you learn integration by parts afterwards. At least that's how your book presents it, so it doesn't have any problems where you have to rotate like x e to the negative x around the x-axis or something. Okay, or let's make it more interesting. That can't make it easier. All right. So this problem, as a math teacher, I really like a problem like this because it forces you to go back and remember your right. Go back to remember your logarithm rules. Because if I just try to say like let u equal the square root of x, right? There's, to maybe try to simplify that before I run to do integration by parts. My du for this one, right, would be 1/2 x to the negative 1/2. There isn't a fraction here, so without doing a lot of work to try to force a fraction here, and I don't think you can, this is not going to work out for you. Okay, this is going to be a mess where you've got ln of a u, and then du, I guess, sort of, but not really du, so you guys still got a dx in there. By the way, if you ever end up with like a u dx, here's a hint, you're screwed up. You can't integrate this, okay, don't do that. So what we're going to have here, okay, is we have to go back and use our rules of exponents. And do you remember, right, that the natural log of AB, right, was equal to the natural log of A plus the natural log of B. Natural log of A over B was equal to the natural log of A minus the natural log of B. And the one we care about is A to the R is equal to R times natural log of A. All right. So natural log of a half, that's really, right, natural log of x to the 1/2 dx. And then this piece here comes down in front. It's not a calculus rule, that is a logarithm rule. Okay. So this comes down in front. This is a logarithm rule. All right. I even give this to my business calculus people. It's a good problem. It's a really good problem because it forces everybody to remember this stuff. All right. And then we have to integrate this, which is what we did on our first example, right? Maybe we should do it one more time just for the sake of completeness, and because you're just learning this and seeing this pattern is probably a good thing. So u is equal to ln x, dv is equal to dx, du is equal to 1 over x, v is equal to x, and then we're going to deal with our box here. So we're going to have, right, uv, so that's x ln x, minus the integral of v du. Okay, so x 1 over x dx. Okay, there's a 1/2 out in front here. So this is going to be 1/2 x ln x minus integral dx. Go ahead and integrate that. X ln x minus x. Let's see. Okay. Does this need to be inside the bracket or can it be outside? Like either or, it's your choice. Okay. I'm going to say that half of the constant is still a constant, and since you get to pick which constant you want, in or out, doesn't matter. Now, these guys both have to be in. All right. But this is a good problem. Okay. Like I said, it forces you to remember all the previous stuff that you got to do, and we'll go through and do that. All right. Let's see, what do we want to do with that? I don't want to do this one too much because, yeah, that's going to go and go and go. So, yeah. Oh, dear. Okay. All right, this one will be fun. All right, so talking about, right, we let's go ahead and take a look at this one just for the sake of it. What was this? This was integral of ln x squared dx. Okay, so just to show you this. This is a good problem too, by the way. Integral of ln x squared dx. All right. Now, you can think about it this way. But since the difficulty in the first place is how to integrate natural log x, breaking them up like this to let u and equal v, it's really not going to help. Okay. So again, really our only choice, the only thing I know how to take a derivative of, the only thing I know how to integrate is going to be this guy here. So our hands are kind of tied. Now, this u is on the outside of the logarithm, not on the inside. You cannot put the 2 out in front here. Okay, so the difference, natural log x squared and natural log x squared. These are not the same. This 2 comes out in front, this one does not. Okay, du is equal to, well, that's 2 ln x times chain rule 1 over x. Okay, dv is still equal to dx, so v is equal to x. Okay, so let's set up our box. Okay, so we have, excuse me, ln x squared minus 2 integral 1 over x times x ln x dx. That cancels, right? So we have ln x squared minus 2 integral ln x dx. Hey, what's the logarithm? What's the integral of ln x? We did that, right? We did that one. So in the interest of time on this one, because I think we've done this twice now, this is going to be minus 2, and we have x ln x minus x. Okay, so here we go with this. We have ln x squared minus 2 x ln x. Okay, plus 2x if you want, plus c. Lots of different ways to write that. Knock yourself out. All right, so there we go. All right, so you've gotten the idea of doing integration by parts twice. Is there anything that says we can't do it 3 times, 4 times, 5 times, and keep going? There is a little bit of a shortcut if you have to do it more than once and you end up with a polynomial like x squared, x to the n, like a power of x, x to the n, times some kind of a transcendental function, like, you know, e to the x or e to the minus x or something. I will show you that one tomorrow. I don't like showing this to classes pretty much because you assume that you could do this with everything, and you can't. Okay, so this is a shortcut for certain situations. All right, and I generally don't like to test on these anyway because people who don't like to learn shortcuts get saddled with doing a lot of extra work. I never liked learning shortcuts. At least for the first time around of learning something, I would rather do it the hard way first, understand it, and then once I understand it, I'm like, okay, I can take a shortcut. So I'll show you this one tomorrow, but also understand that I generally don't pick problems that where this new method is required, but I will show it to you because it is an important thing. Okay, so put this one. Oh, this is going to be too much fun. All right. We're going to need a lot of room. All right. A lot of room for this one. All right. So we have e to the 6th theta sine 7 theta. Okay. So we have e to the 6th theta sine of 7 theta integral d theta. Okay. So here's the thing. When I pick my u and I go to pick my dv, well, this doesn't change, right? When I take the derivative, all I do is get 6 e to the 6th theta, right? And if I take this for my u, then the only thing I do is I get to flip-flop between sine and cosine, and that ain't helping either. All right? So I don't remember which way is always the better way to go with this. There is a preferred method, okay? But you're screwed no matter what you pick, all right? I'm just going to tell you that. You're screwed no matter what. So let's go ahead and it really doesn't matter. So let's just go to sine theta, and then we have dv is equal to e to the 6th theta. Now, whichever way you do pick, you're kind of stuck. So u's are always going to be trig functions now, and dv's are always going to be e's, okay? So don't go back and do it the other way, because we're going to have to do this a couple of times. So du, right? What's the derivative of cosine, or sine rather? Oops. So this is going to be, right, cosine 7 theta. 7 times cosine 7 theta. Now v is going to be 1/6 e to the 6th theta. All right. So think about taking this derivative, right? The derivative of 6 theta is going to be 6e 6 theta. And then since we'll have 6 over 6, that'll work out. Okay. So here we go. We have uv minus v du. Okay. I'm going to go ahead and call this thing I, capital I, not the, I'm not quite on screen. I can't point to my face at my eye and say that I, but no, it's not that I. It's not little I, because that has a job. It's capital I. Okay, so we're going to say uv. So this is 1/6 e to the 6th theta sine 7 theta. Right, there's my uv. Minus, right, integral of v du. So this is going to be 7 over 6. And you could put this inside or outside, right? It doesn't matter. And then we have 7 over 6. 6, there's a 7. And then we have e to the 6 theta cosine 7 theta. You say, oh joy, I've got to integrate this piece now, right? Now I'm in the same bind as I was before. Like, well, let's just crank it through. Maybe something will happen where it gets kind of nice. Okay, so u is equal to cosine 7 theta. Don't mix and match these now, right? You picked this to be e to the 6x, 6 theta. You're stuck with it. Okay, if you go back, you'll end up with like 0 equals 0 or something like that, which is true, but not helpful. Okay, take the derivative of cosine. Well, derivative of cosine is negative sine, right? So this is negative 7 sine 7 theta. Okay, and then of course b here is 1/6 e to the 6 theta. Okay, so going through this again, right? We have this piece. So this is going to be I equals 1/6 e to the 6 theta sine 7 theta minus, all right, however you want to keep track of your sign, SIGN signs is fine, okay, but this is, let's put the 7/6 out here somewhere, okay, we'll have to remember it's there, but we know. All right, so this is going to be 1/6 e to the 6 theta, right, cosine 7 theta, yeah, minus the integral of, let's put a plus in here for this plus, right? Actually, you know what? Let's not do that. It's not pre-process. Let's just process it one thing at a time so we don't lose all of our stuff. So this is minus 7 over 6, right? 7 over 6. And this is e to the 6 theta sine 7 theta. All right. Now I'm going to go ahead and distribute this through, okay, to see what's going on here. So first things first, let's just deal this guy, and this guy is going to turn this into a, it's going to turn that into a plus. Okay. Now we're going to go ahead and distribute this negative sign. So we're going to have, okay, we have I equals 1/6 e to the 6 theta sine 7 theta, okay, minus, this minus gets applied to that, so that's 7 over 36, 6 times 6, e to the 6 theta cosine 7 theta, and it is turned into a plus because of this SIGN sign and this one, so we have minus, it's going to be minus integral 40, let me do this. I don't want to highlight, I want to worry, so that's my job. Okay. So minus 49/36, right? Because that's what this is. Integral, here we go, integral, e to the 6 theta sine 7 theta. And at this point, you will rightly say to yourself, wow, this looks like it's going to go on forever. There's no way out, but there's a way out. So remember, what the heck was I? I was e to the 6 theta sine 7 theta, right? This was integral e to the 6 theta sine 7 theta d theta. Do you see anything that looks like e to the 6 theta sine 7 theta somewhere? That's why we call this I. So this is I is equal to 1/6 e to the 6 theta sine 7 theta, not an integral. So it's not the same thing. Minus 7/36 e to the 6 theta cosine 7 theta minus 49/36 I. You can solve this. Right now, this is back to an algebraic problem. This is one of those problems that you probably did in 7th, 8th, or 9th grade, right? where you swing this thing over to the other side and say this is 49/36 plus 1, I, right, factor that out, is equal to this stuff, right, this stuff, plus C, okay, always with the plus C. And then all that's left is we just have to, we have to get rid of this, right? We have to say, okay, what's 49/36 plus 1? What's 49 plus 36? Looks like that's 85, right? So that's 85/36I is equal to this stuff. So we're going to have I is equal to 36/85 times this mess plus C. Again, constant or 36/85 of a constant is still a constant, so we don't really care. Okay. So we're going to have 1/6 e to the 6 theta sine 7 theta minus 7/36 e to the 6 theta cosine 7 theta. And I guess we could do some simplification here if we really wanted to, but my integral equals, right, d theta is equal to, let's go ahead and do that. So we have 6/85 e to the 6 theta sine 7 theta minus, both of those cancel, so we have minus 7/85, okay, e to the 6 theta cosine 7 theta and plus C. And that is how you do one of those. This class of problem where you have an exponential function times a sine or a cosine, I'll say trig, but what I really mean here is sine or cosine. These all look like this kind of problem where you've got to do the thing twice because you got the on-off switch here, and it flips back and forth, and then you got to swing one over to the other side, and that's very delightful. Okay, lots of places to mess up your SIGN signs, lots of places to mess up your SINE signs. Okay, lots of fun stuff going on here. All right, so I don't even want to check this, right, to go back to make sure it actually works, because I got to do 2 product rules with a bunch of horrible numbers in them. Okay, so I don't even want to check, but that's how you do this class of problem. I guarantee you, it's a rite of passage. Like every Calc 2 problem, every Calc 2 class has a test question that looks like one of these. Okay, it's a rite of passage. So if you ever talk to somebody from any other school that ever took Calc 2, you will be able to both commiserate on the fact that you had to do a problem like this. Okay, so that's I think that's probably enough to talk about today. So go ahead and practice those, and we'll do some more integration by parts tomorrow. Okay, so we'll call it there. I'm going to stop recording.